Professor Christopher, and these, for the next couple hours, my two design teams will be presenting. Those are the last two presentations in here today, so I'm going to let them take the full hour, and then we'll have a break between each one. As I mentioned to some of you before, there are three different aircraft design teachers here, and all do things a little bit differently. Professor Ashworth always does a paper study with the wind tunnel model. Professor Helbling always does some sort of UAV design build test. They certainly do structural tests on it. Ground testing is sometimes part of the plan. Flight testing is optional. I give my students the choice. They could either do the paper study or they could do the flying model. Both teams chose to do the wind tunnel model paper study. Other choices that they have at a very top level are, and very different start. Professor Ashworth always writes his requirement and gives it to the students. Professor Helbling will either write a requirement or he'll go find one for a real commercial system and hand that out. I take a couple of weeks, maybe 3, and let the students develop the requirements. So there's a lot of role playing that goes on in these classes as they go back and forth between acting like the customer sometimes acting like the design contractor. So that will probably come through in what they have to say. So they have a lot of choices. They also get to pick their topic. The topic was subject to some specific constraints. It had to be a manned airplane. It had to have landing gear. It had to have a payload. It could not be battery powered. Those were the biggies.
It had to have a tail.
And basically stay away from exotic stuff like vertical takeoff and landing, hypersonics. Basically, it had to be a conventional airplane suitable for the tools that are available to undergrads here. And without further ado, you now know enough about what they're doing. I'm going to let them tell you what they did. Sherry Gambino was the program manager for what we call the VX program. It's basically a B1, B2, B52 replacement. Her chief engineer was Ricardo Fernandez, and they'll introduce the rest of their team shortly in about an hour and 15 minutes.
Good afternoon, everyone. As Dr. Kazur said, my name is Sri Gambino. I'm the program manager for the YB-3 dataless bomber team. Today we will be giving you our preliminary design review. This is a brief overview of everything we're going to be discussing today. If you have any more questions about any of the items as we go through the presentation, please hold your questions until the end and then raise your hand and we will recognize you. This briefing is to verify that we are prepared to continue into our detailed design phase, where we will actually verify a lot of the information that we are showing you here today. It also answers the United States Air Force's need for a long-range stealth bomber. As you can see, the current bombers used by the United States Air Force are actually listed in this table here. The RFP, or the request for proposal that was released by the Air Force, is actually listed in this column here. You can see all those requirements, where LORCS means Low Observable Radar Cross Section. We'll be using that acronym a lot. We might just shorten it to LO. So if you hear it, now you know what it means. As you can see, all the current bombers that are in use are outdated, and they do not meet the requirements that the Air Force has recently released to the industry. Our design, the YB-3 Aurora, actually does meet those criteria. Next, I'll be handing this over to Ricardo Fernandez, my chief engineer for analysis of alternatives and requirements.
Thank you, Sherry. So, the alternative to designing the YB-3 concept aircraft were, first of all, to redesign the current bomber that the Air Force uses stealth-wise, which is the B-2. This proved to be very costly, and as well, it proved to be a bad option because they only have 19 in service nowadays. And they are looking into acquiring up to 70 aircraft now for the new LRSB program, so that was not a good option. The next idea was either to use unmanned bomber, a new design, unmanned bomber. Now, this is not good because the LRSB project is supposed to be capable of carrying nuclear weapons. And when you have a nuclear weapon, you want to have a human factor in the aircraft. So unmanned aircraft was crossed out as well. That left us with with the manned version of the YB-3 bomber. History has showed us that when the bomber of the Air Force has been outdated, either technologically or by mission requirements, they have requested the design of a new bomber. So that happened for the B-52 being replaced by the B-1, and then it happened for the B-1 being replaced in some missions for the B-2. And this is happening now with the proposal for the LRSP project. Now, the requirements that drove the design for the YB-3 bomber were, first of all, the LO requirements. So that meant that the shape had to be very specific to keep the aircraft as stealth as possible, and as well that it had to have the access panels minimized, so as few as possible, and as well they have to be very specifically located, mostly on top of the aircraft, so top surface of it, so it's as stealthy as possible. The range was a minimum of 7,000 plus nautical miles, a minimum payload of 24,000 pounds for ordnance, and a mission requirement of being able to loiter on top of your target, and as well to have in-flight refueling capabilities. Now I will leave you with Eric Maynard for mission analysis.
Thank you, Ricardo. Okay, I'm Eric Maynard. So this graph here, there's a lot going on, as you can see. We wanted to look at some potential missions that our aircraft would be flying in. So up here, there's a couple potential missions here. The first one is a bombing mission, and the second one is a ferry mission. Now, with these missions, of course, the aircraft starts at its base airport, takes off, ascends to its cruising altitude of about 35,000 feet, and then for its first mission, such as bombing, it'll fly to its target, and then drop its payload, or it may not drop its payload, and you have to carry that all the way back. Its second mission, same takeoff, get to altitude procedure, and then come to descend and land at a different airport. This is good for staging an aircraft for future missions and the capabilities of the global reach of the Air Force. Now, each leg has specific fuel burns that we've estimated and calculated, and other performance parameters which we will go into further detail further on this presentation. I'd like to now hand it off to Jeremy Smith, who will talk about the configuration.
Hi, I'm Jeremy Smith. I'm going to be talking about the development of the configuration for the YB-3. To start out with, we started with some very simple box diagram layouts that allowed us to move the major components of the aircraft around to get very different layouts. 6 of them are shown here, and they show the ordnance bay, flight deck, engines, and empennage surfaces. And please note, this is when we were originally assuming that we would be using 4 low bypass turbofans as the engines, and that decision was changed later. Through a down selection process, we went from these 6 configurations down to 4, and then down to 2, and finally to the final configuration shown behind me now. With a 40-degree leading edge sweep, a V-tail that is all moving, a 30-degree dihedral and 40-degree sweep to match that leading edge, as well as a center-mounted 32-foot reconfigurable bomb bay, and interior-mounted medium bypass turbofan engines. Again, the reason for choosing those engines will be discussed a little later. Shown behind me now are some of the key parameters for the aircraft, including the max gross takeoff weight of 195,000 pounds, a maximum fuel capacity of 92,000 pounds, as well as some of the aerodynamic and geometric parameters. The original parameters for this were estimated using Roscom's aircraft design book, and then refined using the CATIA model, as well as known weights and sizes of things such as avionics and other things that we could put in the aircraft like ordnance. The volume of the fuel was done using the CATIA model and finding the volumetric, the volume of the fuel, and then subtracting 10% of that volume to allow for self-sealing, and that got us our 92,000 pounds of fuel, assuming 6.5 pounds per gallon. I'm now going to hand it off to Eduardo Enrique for a quick comparison.
Thank you, Jeremy. With the max gross takeoff weight of 195,000 pounds, 38% of that was allocated for empty weight, 47% for fuel weight, and 15% for payload weight. When compared to previous aircraft from both U.S. and foreign nations, the YB-3 follows a similar trend, which shows that the YB-3 is heading in the right direction. Amongst these aircraft, B-1B shows the closest resemblance, which shows that the YB-3 is in good condition. All these weight estimates were calculated from both the use of Nikolai and Roscom weight estimations. Now I'll pass it off to Michael Michaelini for aerodynamics.
Thank you, Eduardo. I'll be going over the airfoil selection, some key aerodynamic data, as well as the control surface sizing. We decided to use an eclectic approach when designing our aircraft, taking the similar design to that of the V2 Spirit, with a large triangle portion on the closer side of the fuselage, splitting into a longer thin section. This created two issues, one of which was that we were trying to cruise at a transonic airspeed, which is between Mach 0.75 and Mach 1, and that would require us using a supercritical airfoil, similar to that in the top left. And with the high sweep and shallow chord of the wing, we decided to use a flying wing, as that would have an inherent resistance to twist. When using the design that we had, due to the low observable design, as well as similar to that of the V2, I plugged in various airfoils into a constant aspect ratio of our aircraft to downselect to the supercritical K1 airfoil on the inner main portion of our main wing, and the MH60 airfoil on the outer portion of our wing, which I'll show a little better later. Additionally, for our VTOL, we used a symmetric airfoil NACA 65006, which has a max thickness towards the middle, which should help with our structures for the aircraft, as is a whole moving tail. We used XFlyer 5 to analyze much of our data. This creates some issues, as it's not meant to analyze data in the transonic region. Because of this, we had to analyze data at lower Mach numbers and Reynolds numbers, and try and adjust the data for that to what we have in front of you. The top left shows our CL versus alpha for our entire for our entire aircraft, which has a max CL of 1.2 at a critical angle of attack of 8 degrees. Further, we have a max L over D of 18, and as with our large surfaces that we have in the aircraft, this creates a high drag and higher angles of attack, which actually forces our max L over D at a shallower angle of our 8 degrees. Here's our L over D max plot, which shows how our aircraft performs as we move faster. Approaching Mach 1, it does go down. However, due to the performance of our aircraft, of our engines, it will start to choke at Mach 0.95, which is showed by this red line, which will actually be described later. We used Roscombe and Napolitano to use the equations from those books to find the sizing for our airfoils and, ailerons and flaps. Of this, we found an almost 20-foot lateral span for our aileron with a constant chord of 3.9 feet, and an almost 13-foot lateral span for the flaps with a constant chord of 5.4 feet. We're using split flaps as they perform better for our aircraft, as they do not have the extra holes in the wing that we'd have to try and cover later for the low observable adjustments. As well as for the ailerons, we can use them as flaperons if necessary, as the flaps are sized to perform enough on their own. However, if for emergencies or short field takeoff and landings, they can perform as flaperons for the extra lift. We compared it to the B2, as we used a similar design to see how the ratios compared. And it was very similar. Ours were slightly smaller, but similar in proportion to that of the B2. I'll now hand it off to Alex Warner to talk about propulsion.
Thank you, Mike. So the initial three engines that we looked at were the GE F118-100 low bypass turbofan, currently used on the B2 Spirit, the GE F404-400 low bypass turbofan, used on the F-18 and the F-117, and the F-108 CFM56-2A2 medium bypass turbofan, used on a variety of commercial aircraft, as well as a few military aircraft, such as the KC-135, the E-6 Mercury, and the E-3 AWACS. So we started by taking the sea level parameters for each of the engines, so we could have a comparable comparison. You can see that the F-108 has a thrust output of 24,000 pounds each, which is higher than either of the other two. Similarly, the efficiency of the F-108 is much higher than either of the other two. This is contrasted, however, by the required inlet area for the F-108, which is much larger due to the higher mass flow rate and the higher bypass ratio. This higher bypass ratio, however, of 5.9 is an advantageous quality in terms of LO, Due to the higher amount of free stream air that passes through the engine, our thermal signature is going to be reduced a lot. So, electing to proceed with the F108 CFM56-2A2, we can measure how its performance characteristics change as we increase in altitude. At a cruise speed of at cruise altitude of about 35,000 feet, each engine has a thrust output of 7,500 pounds and decreases to a thrust-specific fuel consumption of about 0.32. Assuming a constant speed and a constant weight as we climb, of our cruise speed, Mach 0.82, the constant weight being our max gross takeoff, we're able to get an estimate using our thrust available versus thrust required calculations for our absolute ceilings. Here you can see that it's about 43,000 feet. However, if we account for the loss in weight due to fuel burn, we have calculated an absolute ceiling of 48,000 feet. So for each engine, there is a specific throttle that correlates with the most efficient fuel burn. For the F108, that is about 70% throttle. However, with our thrust available versus thrust required calculations, we have identified a minimum throttle of 87%. As a result of our engines being embedded in the wing, we require a system of ducting that connects our inlets and nozzles. This is similarly designed to the B2, however, due to the wing of the YB-3 being thinner than that of the B2, our inlet was shifted towards the fuselage. Each of the inlet areas as well as nozzle areas were calculated using software called perf.exe. For LO requirements, the nozzles as well as the inlets have notches cut into them, the angles of which match the leading and trailing edges of the wing. This reduces our radar signature and spikes. Similarly for LO, the face of the inlet must be displaced from the face of the fan face in order to prevent a direct line of sight to the fan face. You can see a small section of the fan blades are still shown. However, we intend to implement turning vanes that will both completely hide the fan face as well as turn the flow and reduce losses. This plot on the lower left is from the YB-3 Survey of Inlet Development for Stealth or Supersonic Tactical Aircraft. Region 1 being a displacement ratio that has well-verified diffuser methods. Region 2 being questionable and Region 3 being non-existent. Using a Z value of 3.5 feet in displacement and a Y value of 3.75 feet of displacement, separating the inlet and the fan face by an X value of 15 feet, we're able to come up with the ratios shown that correlate with this red marker on the plot. Note that the YB-3 is not a supersonic aircraft, however, so this plot just gives us an idea of where we'd like to be heading. Furthermore, to justify our engine choice, we have compiled a list of aircraft that also use CFM56 International Series variants. You can see that the YB-3, both in service ceiling and cruise speed, is very similar to the list shown. However, it's slightly higher, but the important thing is it's not the maximum. We're not pushing the limits. I'll also note that this is service ceiling of 47,000 feet, but our cruise ceiling is 35,000 feet. I'll now hand it off to Eric Maynard for performance.
Thank you, Alex. Okay, the first graph for performance is a constraints diagram. This basically allowed us to take a look and see where we actually wanted to push the design of the aircraft. First thing you'll notice is this reddish orange line here. That's our takeoff parameter, and the blue line is our landing parameter. And those two parameters are the ones that are driving our constraints. Anything above the takeoff and to the left of the landing is a favorable design area. Now, for these to get an optimal design point, you want to be as low and far to the right as possible, which puts us right about there, at a wing loading of 75 pounds per square foot and a thrust-to-weight ratio of about 0.31, 0.32. This next diagram is our specific excess power plot. This basically shows the regime in which our aircraft can fly at altitude and at what speed. So the P sub S of 0 here, this blue line, basically shows at that point we have no excess power, so we can't really change our flight dynamic. We can't go much slower, we can't go much higher. Now, a couple things to note about this. The dashed blue line here is at Mach 0.95. That's the area of, that's the line of its maximum speed. Any faster, the engine will begin to choke due to shock waves. And of course, an absolute maximum speed of Mach 1. And from that point, we can also conclude that our maximum altitude is about 48,000 feet. And that's due to some loss in weight as well with calculated field burn. The next diagram is a turning diagram. Now here we can see the maneuverability of our aircraft. Now, we're not a fighter, so we don't have to have high maneuverability. We're not looking to pull a 7G turn. However, our aircraft can sustain a maximum load factor of 3 Gs, a minimum speed of Mach 0.41, and all this is at an altitude of 35,000 feet. Our minimum turn radius is about 8,500 feet, and of course, again, our maximum speed is about Mach 0.95. And since we won't be flying to these maximum limits, most of our flight regime will be done within this green circle here in the bottom. Now, the final graph here basically explains the last of our performance parameters. Starting from the bottom, you can see our takeoff and landing rolling distances. Our takeoff distance is about 5,300 feet, and our landing distance of 7,800 feet. Now, these are with clean configurations, meaning no flaps, no thrust reverse, nothing like that. A couple other parameters, our cruising altitude, 35,000 feet. Our absolute ceiling is 48,000 feet. Again, that's with calculated field burn. And our service ceiling of 47,000 feet, which gives us a rate of climb, if necessary, of 100 feet per minute. The final two things to know is our range and our endurance. We get a maximum range of 11,800 nautical miles and a maximum endurance of 24 hours. All these parameters are done with the constants shown here in the upper right-hand corner. And all these values are calculated by the equations used by John Anderson in his book on aircraft performance and design. I'll now pass it off to Eduardo Enrique, who will talk about the stability features of the aircraft.
Thank you, Craig. By arranging the weights of the YB-3 managed to get a CG location from the nose of 49 feet with max payload, and with no payload, it's 49.4. This corresponds to a 14 and 13% static margin, respectively. This is only a 1% static margin change, which means that the YB-3 will become more maneuverable during flight. Taking to mind that Roscom says that anywhere between 10 to 15% static margin is acceptable for a large aircraft. When taking into consideration fuel burn on the left, you can see the large change in CG travel due to the fuel for both no payload and max payload. This corresponds to the large SM travel as well, starting from 100% of fuel capacity down to 10%, which corresponds to a 2% static margin. This means that the YB-3 becomes extremely maneuverable during flight while burning fuel. However, the YB-3 is still statically stable due to the fact that a stable aircraft is considered stable when the SM static margin is above 0. However, to mitigate such a large travel in CG, the fuel closest aft can be burned first, or you can use a series of fuel pumps to shift the fuel forward, and as a result, adjust the SM travel as well. When sizing the VTOL of the YB-3, it was essential to maintain the 30-degree dihedral due to LO purposes. As a result, it was only essential to size the effective horizontal tailspan, which corresponded to a negative 0.863 per radian. This is at a horizontal tailspan of 35 feet, and for any value that is less than 0 for CM alpha, it is considered stable. Note that any value for effective horizontal tailspan results in a stable aircraft. Therefore, the YB-3 is inherently longitudinally stable. However, when taken into consideration the lateral directional stability, it was essential to maintain some stability. Therefore, it was essential to maintain 35 feet for effective horizontal tailspan, which corresponded to a negative 0.079 per radian, which is marginally close to the typical ranges for subsonic aircraft. As for CM beta, we managed to get a value of 0.138 per radian, which is well within the typical ranges for subsonic aircraft. In the event of an engine out scenario, the YB-3 only needs to travel at 200 feet per second to maintain control of its control surfaces, which is well below the stall velocity of 366 feet per second. This means that the YB-3 will stall before it ever loses control of its surfaces. This is favorable during takeoff, which means that the YB-3 can easily maneuver into a safe zone. As for spin recovery, due to the fact that the YB-3 does not have a horizontal tail, that means that the effective horizontal tail does not get shielded due to the horizontal tail. The only things that need to take into consideration are the wing and the fuselage itself that may pose a threat. However, the YB-3, the vertical tail only has to, 2/3 of it cannot be shielded. Therefore, the YB-3 is fine as far as the wing and fuselage being shielded. I'll pass it off to Alex Warner, who will go over structures.
Thank you, Ed. So all of the structural components shown in red for the YB-3 are comprised of 7075-T6 aluminum box beams. This is resulting in a total structural weight of 30,300 pounds. The ribs sizing and spacing that you see was taken from the Roscom Volume 3 aircraft design, as well as basic structural design taken from similar aircraft structural colorways. As far as mission versatility goes, we have a reconfigurable bomb bay, which involves replacing and interchanging the key structural bulkheads within the bomb bay to incorporate both two 15-foot rotary launchers as well as three 10-foot rotary launchers. As a result of our all-moving tail, we have calculated a pin diameter of 12 inches. And similarly, we have a pressurized cabin that enables the crew of the aircraft to maintain steady pressures and temperatures. In order to mitigate risk, we have performed finite element analysis on key structural parts of the aircraft. Here we have the main body of the fuselage. You can see we modeled both engines, each weighing 4,800 pounds. The maximum payload weight in the bomb bay, 30,000 pounds. And the force of lift at the root of the wing that we equated to the weight of the aircraft. For these calculations, we have applied a 3G loading as well as a factor of safety of 1.5 to all loads. For 7075-T6, the ultimate tensile stress taken from our CEM EduPack is 76 KSI. However, you can see that on the main body of the YB-3, there's a max stress of about 40 KSI. Similar calculations were performed on the wing. The loads seen were used by our lift distribution, pulled from Schrank's approximation, which was calculated during the course of the semester. Again, a 3G loading was applied, as well as a 1.5 factor of safety. You can see that, again, assuming lift equals weight, that our max stress is about 65 KSI, which is still below our 76 KSI limit. For LO purposes, we have as few access panels on the bottom of the aircraft as possible. Those that are required, however, perform multiple uses. For example, these two lower ones provide both landing gear deployment, as well as engine access, fuel access in the wings, and any hydraulics or electrical maintenance that may be required. Similarly, the forwardmost access panel provides forward landing gear deployment, as well as crew access and avionics access. All other access panels are located on top of the aircraft. These boxes here just show general locations, it's not actual size. which will give maintenance ability to hydraulics in the wing, fuel that's in the wing, as well as electronics. We have an in-flight refueling port located at our forwardmost fuel tank, just aft of the flight deck, that supports our in-flight refueling capabilities. In order to support our maximum fuel weight of 92,000 pounds, we have the fuel located on the YB-3 as shown in figure 43, with fuel both in the fuselage, the tail, the wings, and around the bomb bay. I'll now hand it off to Cherie Gambino for structural constraint analysis.
Thank you, Alex. As you can see here, we have the flight envelope for the YB-3 bomber. We have it shown at 3 different elevations. We have sea level, 35,000 feet, which is our cruise altitude, and also 48,000 feet, which is our absolute ceiling for the aircraft. What this diagram is showing us is that when we are flying at our cruise speed of 0.82 Mach, we are not going to be up in this region. We cannot hit around a 2G loading, as at that point a structural member would start to fail. It is also shown again for sea level, so during takeoff, you'd be operating in this speed range with very low Gs. And up in this area is an inoperable area because the actual performance limit due to the engines is at 0.5 Mach, which is in this region. On the next slide, we have a Venn diagram. This diagram is showing that our design at our cruise elevation is not driven by gusts. So if the aircraft was to encounter turbulence at any point, no structural members would fail. And we know this because there is a, Federal Aviation Regulation 23 that states that these gust lines at 66 feet per second, 50 feet per second, 25 feet per second, and then their negative corresponding values must be contained within the envelope. As you can see here, they are all within the envelope, and at our operating velocity, our cruise velocity, the envelope here is actually above that line. Additionally, it shows our maneuver velocity as 0.4 Mach. The maneuver velocity is actually in this corner right here. Next, I will hand it over to Ricardo Fernandez for landing gear.
Thank you, Cherie. We will now go over landing gear location, main landing gear design, and shock absorber sizing. All of the following was done using Daniel Raymer's aircraft design book. So here we have the overview below, from the bottom of the aircraft. We have the main landing gear here, and the nose gear here. We have as well the location of the most FCG, which is important to note that FCG is only when the aircraft is completely empty. So it's really not going to be happening very often. Sorry. Here's the most forward CG, and that corresponds to when the aircraft is at its max gross takeoff weight. Even though the most FCG looks like it's almost right in the center of the main landing gears, it's still in the front. It's just that the representation picture is enlarged. It is important for the landing gear to be behind because you want to prevent the aircraft to tip back. The aircraft as well has to be able to rotate. So in the following image, we have the clearance for rotation of the aircraft, clearing the tail. It's a 14.38 degree. Our aircraft is designed to rotate at 10 degrees for takeoff, so that means we have a clearance of 4.38 degrees. It is not very large, but it is a considerable amount, and there is going to be a control law that will prevent the pilot from pulling the aircraft onto the ground, either on takeoff or on landing. As well, it is important to note the distance from the floor to the body is larger than 10 feet, which is enough to be able to load the bomb bay, so you can put a cart with the bombs and into the bay. As well, you can see here the most aft and most forward CG. It's important to note as well the difference in between the two. We'll explain about that later. Here is the lateral tip over criteria. You don't want your aircraft to tip, while on ground operation, you don't want your aircraft to tip to the side or forward to the side. So you want this angle to be stated by Daniel Raymer's book, less than 45 degrees. Our aircraft meets that requirement, being at 44.68 degrees. We have to keep it close to the limit because we need that clearance to be able to load the bomb bay without any external lifting capabilities of the aircraft. Due to that CG we were talking about, that big difference of CG that is really due to the large payload we have in the aircraft, we were worried about the aircraft not being able to rotate on takeoff, having the max gross takeoff weight being so much forward from the CG, but having to have the most aft CG as well forward from the landing gear, because you don't want it to tip back when it's empty on the tarmac. So this orange line shows the moment created over the main landing gear by the max gross takeoff weight of the aircraft, and this blue line shows the created by the deflection of the tail over as well the main landing gear. So this red area is where you couldn't place your landing gear because the aircraft wouldn't be able to rotate with its control surfaces, and the green area is where they would be able to rotate. Our landing gear is placed right there at 56.7 degrees, feet from the X direction. So we're on the green area. As far as the main landing gear design, we went with an inline 3-wheel design. It is not a very common design, but due to volumetric constraints, mostly on the y-axis, because we have the engine right there on the wing and all the fuel tanks, it was difficult to place just a conventional bogie landing gear. So we went for 3 inline, and it's smaller wheels as well, 3 of them, because our wing is so thin, and we didn't want to have any extra protrusions on the surfaces for stealth capabilities, to keep the stealth good. So we kept the wheels as small as possible. It's with 3 of them we can support. We went onto the Michelin's catalog, which shows a 36-inch radial landing gear, which is way more capable than the max static weight onto each of these wheels. As well, we went on to following as well Daniel Raymer's book. We went on to shock oleo shock absorber sizing. The minimum required stroke is a 6.29 inches and a aluminum piston diameter of 18.7. This will be further developed on detail design by probably choosing one from a catalog. As this aircraft is trying to keep the cost as low as possible, we want to choose stuff that is out of the box of the manufacturer. Now I will leave you with ordnance bay and flight deck. With Jeremy's name.
Thank you, Ricardo. I'm going to be talking about the ordnance bay of the YB-3 as well as the flight deck and avionics. As previously mentioned, the ordnance bay is 32 feet long and reconfigurable. And what that means is we can have 2 15-foot rotary launchers or 3 10-foot rotary launchers, each having 8 weapons pylons and weighing over 1,000 pounds each. As previously mentioned, we can carry a total payload of 30,000 pounds in the payload bay. However, we can only carry 24,000 pounds of ordnance due to the weight of these rotary launchers as well as the supporting structure. The YB-3 is designed to carry most current U.S. Air Force conventional, nuclear, and thermonuclear ordnance, a short list of which is shown here, though this is not by any means an all-encompassing list. The flight deck of the YB-3 is designed to hold 3 crew, a pilot, co-pilot, and electronic warfare officer. The ERAU station is designed to meet the Air Force's requirement for a multi-role aircraft, as they like these days, as well as fit the role of a spare pilot station for long endurance missions. Long endurance missions usually have a spare pilot on the B-2, and the difference with this is the B-2 has that spare pilot sit in a jump seat at the back of the cockpit. We have them seated in an ejection seat, which is a drastic improvement in crew safety. The avionics of the YB-3 are designed to be modular and easily removable and replaceable by ground crew for improvements, as well as for repair. A little mock-up of the flight deck is shown here. That is definitely not complete, but that will be improved upon in detail. Also shown the 24-volt, 35-amp-hour Concorde battery chosen to be used on this aircraft. I'm now going to leave you with Sri Gambino for the risk reduction.
Thank you, Jeremy. As we were using rotary launchers for our ordnance, the first risk reduction area we looked at was in bringing a different system into the aircraft. So the 2 options we looked at were a deadweight drop and a free stream release. Deadweight drop actually has a major issue for smaller ordnances, as if you are releasing that piece of ordnance from the bomb bay, there's the potential that the force of the free stream will actually force the ordnance back into the bomb bay and cause some serious problems for the pilot. So that was quickly thrown out. We also looked at free stream release, which would essentially be a system very similar to the rotary launcher, being lowered into the free stream, and then bombs could be rotated and released from that rack. However, this drastically would decrease performance as it increases drag significantly. As a result, we decided to continue with the rotary launcher, as although there is a weight penalty associated with it, it is a proven and reliable system to use. However, there are risks associated with it as well. There's a risk called a hung store, which is essentially a piece of ordnance that is given the command to separate from the bomb bay, but does not actually separate. So in order to mitigate this risk, so we can continue to use that rotary launcher, there will be a recommended secondary locking system, which is a simple modification to the existing rotary launchers that can actually deploy to lock that piece of ordnance in place, and then the rotary launcher can be rotated and used for another piece of ordnance to be deployed. The other risk reduction we looked at was as far as avionics goes. We were looking into using modular units, which will help reduce the cost as well as the upgrade risk and integration risk on the aircraft. We also looked at landing gear rotation problems that will be solved by using a control law. And of course, our maneuver limits will be enforced by a control law as well. Our fuel pump system will be used to regulate the CG and static margin shift during flight, and engine failure scenarios will be mitigated by the Kevlar construction of the cowling. So if a turbine blade was to ever be ejected from the engine, it would not significantly damage the wing. Our basic conclusion was that yes, this aircraft, this design is convergent, and what we highly recommend doing is going into our detailed design phase and building a scaled model that we can alter geometry on, deploy landing gear, deploy flaps, and different things like that, in order to verify all of the numbers that we have shown you here today. This is a summary of everything we talked about. Are there any questions? Before you guys do questions, we would like to acknowledge some professors. I forgot to say this at the end. We'd like to acknowledge Dr. Brenda Haven, who's actually sitting here with us today. She helped us with all of our engine and performance stuff. Dr. Traub, who isn't here unfortunately, he helped us with all of the airfoil selection. And last but not least, Dr. Chrysler for helping us get this whole thing brought together. So thank you.
Okay, I've got a couple
I think Dr. Chrysler has a mic up there.
Okay, okay, really good presentation.
Thank you.
Lots of information, really smooth in terms of the handoff. So it was very enjoyable.
Thank you.
I do have a couple of engine questions. Hi, Alex. Very challenging putting I would consider a high bypass ratio turbofan engine into a embedded design. Your serpentine inlet coming from the top of the aircraft is got a little bit of curvature to it. Okay, so any idea about how you're going to handle the boundary layer buildup on that inlet?
Oh, so towards the fan face, we actually will be implementing the small boundary layer section from the pores in the ducting itself.
Okay, how are you generating the suction? Or any ideas?
From the bypass flow. It's something we will be looking into further in detail.
It's not modeled on there, so that's not a very good
Okay, so you have basically an opening in your engine case that allows the higher velocity fan flow to create a lower pressure.
Correct.
Okay. Your exits. Now the area of that exit is, what was that based on?
So that came directly from perf. So we were able to model the engine with its MDOTs and all the parameters of the engine, and So one of the outputs that perf has is the areas of the nozzle plus 18, or the stage 18.
Okay.
That gave us the total cross-sectional area.
Okay, so you took your, so it's not a mixed flow, it's a, well, it is a mixed flow, but you use separate flow results, like the mass flow rate at the temperature at the exit of the fan, and you added that area to the exit of the core.
Yes.
Okay. So you've got a fairly long, a long duct, and what do you expect to happen to the total pressure as it goes through that duct?
It's probably going to increase since it's
Total pressure.
oh,
In other words, you're going the wrong direction.
it's going to decrease.
It'll decrease a little bit, so just be aware that the total properties that perf gives you is maybe a little bit optimistic. When you start putting a longer duct, you may need a little bit more area
Okay.
to pass the mass step.
We intend to further analyze the ducting,
Okay.
the inlets and nozzles in detail.
Okay. The duct placement, slide 28. I like your wording. Not really. You said that puts us in the questionable region of the inlet geometry, or the basically your delta Y over delta Z. So you've got a pretty big offset in both directions. Is that really the questionable region?
So it's not so much as questionable as there's further diffuser methods required.
Okay, so more advanced.
Right, exactly.
Okay, don't say questionable, because the question then becomes, why did you say something that's questionable?
So
Yeah, it's just more, you can't do it with a fairly simple models. You probably need to use computational fluids, a well vetted program to determine. Let's see. Your detail.
Slide.
Just in general, they look pretty skinny. And you got a 12-inch diameter pin, so pretty hard to see what the scaling is on that. So there's enough volume in there to give you a lot of strength.
Oh,
We actually
So-
do have some analysis on that detail
Okay.
that we can show you in class.
It works. There we go.
yeah. So we did model the V-tail, or the tail of the YB-3 using our finite element analysis. For these forces, we generally just use the moment to create turning for both takeoff and landing of the aircraft. And as you can see, there's a maximum stress of about 33 KSI that happens where that pin is located in this green
And what's your margin of safety then for that?
1.5.
Okay. So what
Or
happens
the
when you
factor of safety.
what happens when you have an engine out?
Well, since they're very close to our seat,
Since the engine's out, is that what you're talking about?
Yeah, so what was the question again?
Engine out. If you're looking at, your loads are going to be greater, right?
Yeah, so in the event of engine out scenario, due to the fact that the engines are so close to the midline of the aircraft, one single engine isn't causing that much of a moment. So therefore, due to the size of the V-tail, it could easily correct it.
Okay, within that 1.5 safety factor.
Yes, ma'am.
Okay.
Definitely.
And then the last question is, looking at your constraint diagram, you have a takeoff requirement at Mach 0.22.
Yeah, it's slide.
That's slide number 31. Okay, so that's your constraint, and so that is pretty. I mean, it's pretty big compared to everything else going on. And so, what's the driver of that particular line?
The takeoff parameter?
Well, the takeoff at Mach 0.22.
Okay, so that's basically it. That's at sea level with the stall velocity, or just above the stall velocity. So it could rotate and take off. That was why it's a little higher. And it's, I assumed a G of about 1.15.
Okay, is that your acceleration?
Or no,
You have an acceleration there of.
the acceleration is 7 feet per second squared.
Yeah, why? Is that a choice or is that a constraint or what is that?
That's taken from data of other aircraft. It's just an estimation, more or less. So
And what does that allow you to do?
that gives us basically our takeoff or one distance essentially.
Okay, so that's your acceleration along that's what drives the distance that it takes you to
Right.
accelerate to Mach 0.22.
Correct.
That's sea level.
Correct.
Okay. What about at 5,000, 10,000 feet?
5,000 those weren't calculated yet. Those will be analyzed further in detail once.
Okay. Okay, thank you very much.
Good job with the presentation. I just have a few questions here. We'll start on slide 4. One thing I would like to have seen here, instead of just putting an X saying that you met it, that requirement, show me how you met it. Like, what's your number for your payload?
It's
Well,
actually 24,000 pounds.
yeah, but if you put that in there, it just helps me know how you actually met that.
Thank you.
The slide 5 and also the slide 24 and 29, I like all analysis of alternatives. I think that's awesome. You're the first group I've seen do that.
Thank you.
So it's a really good place to start when designing some stuff. So good job.
Thank you very much.
Slide 11. If you could color code that or find a way to make it more easy to read, like what part of the engine, which is the payload, that type of thing, it just makes it more clear.
Do that for detail.
Slide 13. So I added up your numbers. The 73 and the 92, you get 165,000 pounds.
We were told, you want me to take that?
I'll go ahead and do it.
Oh.
Based on some feedback that we got, we were told not to put the weights down to the pound. We were told just to conserve the significant digits and give the overall large numbers. So for our total gross takeoff weight, it's actually 195,307 pounds. And then the max fuel weight is 92,220 pounds.
Here's what I'm getting at. So I get 165,000, right? So a difference of 30,000 pounds. You said your payload capacity is 24,000.
Plus the weight of the rotary launchers
Yes.
and all the supporting structure.
Okay.
Sorry, payload is 30,000, ordnance is 24,000. Sorry.
Okay, I got you. So the ordinance is 24 plus whatever. That makes up the difference. Okay. That makes sense now. Slide 36. With the CG stuff, it would be beneficial to see, instead of just those 2 points, maybe showing how over the course of your mission, how your CG changes. Okay, you take off, you fuel burn, now I drop payload, how's the CG change, and then how does it change as I go home? That kind of thing. You just show it over the course of a flight. Over a mission. I know it's kind of shown on the next slide a little bit.
It does. The reason why it's like that is due to the fact that every mission will range differently. So this gives you an example for every single fuel capacity. It will show you what would happen had the payload been dropped. So this is just a general idea over like any mission. And as of now, we don't know what the actual fuel capacity is going to be when the payload is dropped. So that's why we did that.
Okay. Going back to some engine stuff, did you guys look at single engine numbers for takeoff and landing and what your minimum runway requirements would be?
No.
So,
I think we assumed that if you only have one engine, you probably wouldn't want to try taking off. But if that's something that's typically done in industry.
okay, so say you refuse to take off and then you'd have to brake, so how long would that runway have to
Oh,
be?
you're talking about engine failure during roll.
Yeah.
Oh, is that?
Yeah. You go power up, you go into and roll, you lose an engine. Can you take off? Or if you're gonna board it, how long a runway do you need?
So with the, can you go to the fourth one? Or 34?
We did do that.
Yeah, so here, these takeoffs, takeoff and landing distances, they're both with clean configurations. So yeah, it's a big number to have 7,800 feet, but with the deployment of flaps, that would probably come down like 1,000 feet or so. So we were looking at some of the world's longest runways, about 10 to 12,000 feet. So we were looking at longer.
A good average of a lot of the Air Force runways that we looked at were about 12. A lot of the runways that we looked at were about 12,000 feet for larger aircraft that took off them. Some got up to 13, and even like very few were even up to 14,000. But we took it about 12 to 13,000 as the runway distance that we would have to take off from. So with that, it would have enough distance to stop, like up to full rotation.
So then to answer your question, we're looking closer to 10,000 feet in total in case of an engine out.
Okay.
We guys can have a radar on board, and we do account for that CG and the weight.
That's actually counted for in the avionics.
Okay.
What was the Bombay door design? I didn't see anything with that.
That's because they weren't shown. So initially, if I go to one of these, let's see if we can show it. Okay, I guess this kind of shows it. So right there in the middle where you see the CG, that's with the bomb bay doors closed, obviously. We consider the actual design of the doors themselves to be something to be done in detail, and in fact something we will definitely be doing in detail. But as far as actually modeling them right now, it's kind of beyond the scope and beyond the time frame that we had. The bomb bay doors was just kind of a traditional open and close. We originally thought about trying to do one where they pulled up inside and swept open, which we may still look at, but for now that hasn't been fully processed.
Okay, just curious. That's all I got.
Yeah, one more question about the thrust vectoring. Okay, during the thrust reversal, it only is out the bottom.
Yes.
Okay, so how's that going to happen?
So a lot of the CFM 56 series have built-in thrust reversal capabilities. So what would we have is we'd end up modeling, designing ducting that would lead from the nozzle portion and down through the landing gear door bay. Right? Yeah, the landing gear access panels.
So this is after the two streams have mixed?
Yeah.
Just be bypass.
Or is it?
Yeah.
That would be just bypass.
Just bypass.
We talked about this. It was just bypass flow.
Okay, so if it's just bypass flow and you're only doing it down, what happens to the top part of the flow in the top part of the engine? It just continues. You're just gonna reverse half of that, or
So that was kind of more my department as far as the modeling, which again hasn't been done yet. It's going to be done more in detail. So the bypass reverse thrust that we looked at for a lot of the CFMs, it's not a clamshell, but it's the type where they move back and move in to block that free stream. We would then have a duct around that ducts all of that air down and out the bottom, so it would be virtually all of the bypass flow that is ducted out the bottom.
so the top stuff is going to come around in an outside duct that's going to then.
Yeah, more or less. The upper flow and around the sides is going to be ducted down or out the bottom, and there will probably be quite a bit of loss in that. But the whole idea that we were told, actually, when talking to Dr. Chrysler a little bit about it, was that a lot of reverse thrust works in the absorbing of momentum more than the vectoring of thrust the other direction.
Hit the wall, basically.
Exactly.
Okay, thank you.
Sorry, I totally forgot about this. Slide 62. It's also on slide 63. There's no I in ordnance.
Oh, I circle that every time.
Yeah.
You got it right.
So yeah, the engine people before it got right. So that's the law. You remove the I, that refers to weapons.
Thank you.
We will be sure to fire our chief.
Any comments? Any other faculty?
Overall, good job, guys. I do have a few questions. Not much of an airplane expert, but I do know presentations. I thought you guys did a great job of looking at comparable aircraft, your historical review, and going back to your historical comparables in many points throughout your presentation. However, I noticed when it came to a couple of places, notably aerodynamics and lift alpha curves, and where there was no comparison made to previous aircraft. So I wanted to know, where does looks like a 7.5, 7.75 degree stall angle fit in with your previous bomber iterations?
The problem with that is actually the bombers that are currently in use by the Air Force, all that information is classified. So we really didn't have anything to go off of there besides our analysis tools that I'll actually let Max talk more about right now.
I did try and look at other aircraft to try and have some sort of estimate, especially because I had to add corrections and try and adjust the data from where I could analyze it. A lot of things were either just not given or kind of fudge factored, in that I'd have one number here, another number just seemed completely different. So it was kind of hard to actually find comparable aero data for things like such as the B-2, which is what we felt that our aircraft was a little more comparable to.
Okay, but what did you think? What kind of a range did you come up with your estimations? Was it 2 to 20 degrees? Was it 15 to 20 degrees?
I don't know.
That information isn't out there, it's classified.
All right, I'll move on to the engines, which was the other one where comparisons were made to other aircraft which use that engines, but those were typically transport category aircraft and not stealthy military bombers.
Yeah, so this,
So, yeah, exactly. And Professor Christian pointed out my follow-on question, which was, has this engine ever been ducted before?
no, it hasn't. So, had this been for in a professional setting for a large company, we would recommend research and development of.
So do I.
Yeah, which we are unable to perform.
Oh, okay.
Beyond the scope.
Of course.
That's a reason. It's the reason that we decided to take as a group, but as well, other medium bypass turbofans have been used in a wing. For example, I think the DC-11 has one on the tail, so it is possible to dock a medium bypass. It's just not very common. And well, in a stealth aircraft, yes, we think it has not been done.
And what was the shape of that?
Oh,
It wasn't.
well, actually, the DC-10 does have a curve.
Yeah.
Also bottom.
I stand corrected, it was an Esther. Okay.
If the numbers support it, at this point, we can do it.
Okay.
It's a potential.
All right, so I have two main concerns with your engine, and Professor Hayden said very well, which are, where is your aircraft in performance of its thrust and ceiling compared to other similar aircraft? And are you going to be able to get the thrust that you want out of this ducting situation? Hold that for a moment. The question came up about where does your boundary layer suction come from? And it comes from the bypass. Now, what do you do in the case of an engine stall, whether it's temporary due to a gust or an actual engine stall, and now you don't have that suction source to reattach or shrink your boundary layer?
That would just create extra drag on that side of the engine out area as location, but we don't know the drag of the inlet yet. We assume some losses for the engine wise, but we don't know the drag in the inlet completely. And that's part of our wind tunnel testing that we're going to be doing next semester. So we will actually calculate what happens if you have no suction, what's the max drag that you get from that inlet, and we can add that to the drag created by the engine and the engine out scenario.
Okay, I wasn't referring simply to the loss through the duct, but the actual loss of function of your engine.
That's why we have our engine out scenarios done with SMC. So essentially, the recovery would occur of the aircraft, so you would decrease elevation and speed until that engine within the ducting was no longer stalled, and you could get back your operation of that engine, essentially.
Okay, I have one last brief question, pass on to Professor Chrysler, which is, I know that all professional pilots make perfect landings, and that's probably so for the Air Force pilots. What are the side loads on those landing gears?
No side loads have been calculated. I was following preliminary design for the landing gear. Side loads are not part of it, at least not on Raymer's or Ruscom's book. So that will be further developed, as well as all the mechanisms for retracting landing gear for the landing indoors, and as well for shock absorber. Shock absorber is still in a preliminary phase.
Take some questions from the audience. Anything you want to ask?
You can all ask questions. I'm sure you have some. Come on, it wasn't that good.
Well, that's it.